Hello, Algebra 1 CP students. Hopefully you're having a good day so far. Today, I would like to go through a couple of test review problems for you as you prepare for the summative assessment on inequalities. The summative assessment entails solving and graphing regular old inequalities, just like this one-sided inequalities, solving and graphing compound inequalities, like this one with or and the problem with and on the back side of this page, as well as word problems involving inequalities. All right. The summative assessment is broken up into two pieces for you. The first piece you will be taking on either Thursday or Friday, depending if you're in Group A or B. And that first piece is just on solving and graphing compound inequalities. Nothing to do with word problems on that first piece. The second piece that you'll be doing on Monday, which is a virtual day for everybody, it'll be a take-home piece. That part will be just solely focused on the word problems. Okay, so it's kind of nice. You only have to worry about the solving and graphing of regular and compound inequalities on that first Thursday or Friday. My logic is that sort of chunks it for you into smaller pieces, so it's a little bit more manageable rather than preparing for everything all at once. So what I'd like to do today, like I said, is highlight a couple of those problems for you. I selected some problems from the test review, which is posted on Google Classroom, by the way, along with the answer key. It was made by our instructional assistant, Diana, and I think she did a wonderful job. So I kind of just picked a couple of them that I think highlight some really important things that we've talked about throughout this unit, and I'd like to go through them with you. I believe there are 7 problems here, 4 on the front and 3 on the back. So let's not waste any more time. Let's get right into it. If you do have any questions, though, at any point, please feel free to send me an email or just let me know. All right, starting with the first problem, question 1. Try to write the inequality represented by the graph. So if I look at this graph here, I would see that we have an open circle at 4, correct? So clearly, we're talking about all the values related to 4 somehow. Are the values on this inequality graph, though, bigger than 4 or less than 4? Well, the answer to that is that they'd clearly be bigger than 4 because we're shading to the right. Remember, the right kind of represents the fact that we're greater than 4, and the left represents the fact that we're less than 4. Okay, so I would say here that this inequality, all the values for x that are shaded in are those that are bigger than 4. And notice I did not say greater than or equal to because, again, we have that open circle. Hopefully that makes sense. Just a regular old one-sided inequality. Problem number 3 here is a compound inequality graph that we need to identify. Notice that since we're looking for this overlapping region between two values, that's exactly what we see when we deal with and style problems, correct? So we know that x is between 2 and 6. It's greater than or equal to 2 because if you notice, it's on the right side, shading to the right side of 2 and shading to the left side of 6. So we'd be able to say that x is greater than or equal to 2, closed circle meaning greater than or equal to, and at the same time, x needs to be less than 6. Just less than because we have that open circle. All right, so those are the graphs that we've seen when we've solved problems and had to graph them. It's just kind of asking you to go in reverse. Hopefully that makes sense. Let's now transition to some of the solving and graphing inequalities. Here's just a regular one-sided inequality. Nothing fancy going on here. This should be a problem that we're more than comfortable with dealing with at this point. Just to go through it quickly with you, the first thing I'm going to do on that right-hand side is I am going to distribute. We're going to take that 6 and multiply here to clean things up a little bit. This is going to give me 6 times 5 is 30. 6 times negative 3x minus 18x, so 30 minus 18x minus 2x, just going to carry straight down. I'm going to combine like terms on that right side. We get negative 6x minus 82, it's less than or equal to. Negative 18x minus 2x, we're going to get 30 minus 20x. Now, if you notice, again, these are the like terms that combine to give us the 20x, right? If you notice, we don't have any more like terms to combine. We have variables on both sides, so you do have a choice at this particular junction. You could choose to either add 20x here and here to eliminate the minus 20x, get all the variables on this side, or you could certainly choose to add 6x here and here, eliminate the minus 6x here, and get all the variables on this side. I would personally choose to add 20x to both sides. I think that is definitely the way to go here because not only does it get all the variables on the left side, which I think a lot of students are more comfortable with anyway, it also gets a positive coefficient for x, which I think is really convenient. So we get 14x minus 82 is less than or equal to 30 by adding 20x to both sides. And now this has become a two-step inequality that we know and love. Love solving two-step inequalities. They're nice and familiar. I'll add 82 to both sides. I get 14 is less than or equal to 30 plus 82 is 112. 14x, sorry. 14x is less than or equal to 112. Last but not least, we'll divide by 14 to get x alone. And I believe this comes out to be that x is less than or equal to 8. But let me just double check my calculator here. If I do 112 divided by 14, we get 8. Just wanted to double check. X is less than or equal to 8. Hopefully that made sense. Now I can go ahead and sketch a graph of that. Say x is less than or equal to 8. If this is 8 on the number line, we would have a closed circle because we're less than or equal to. Maybe we're going to shade that in because it includes 8. And we're going to shade everything to the left because all these values are those that are less than or equal to 8. Okie doke. Now transitioning to a compound inequality. If you notice, a compound inequality is really very similar to a regular inequality. It just so happens that you're solving two of them at once and representing them both together on a number line. So let's take a look at what that's going to look like here. In order to solve this, I would subtract 2 from both sides, right, because we want to get the 5x alone. It gives us 5x is greater than or equal to 50, 50 minus 2. Dividing both sides by 5 to undo that multiplication of 5 times x, we would end up with x is greater than or equal to 10. So that's the first piece here in this OR problem. Second piece, we're going to go through similar steps. Get x alone by subtracting 7 from both sides. That gives us the opposite of x is greater than negative 9. And now to lastly undo that multiplication of negative 1 times x, we can divide both sides by negative 1 and get that x is less than, notice the inequality is going to flip because we divided by a negative, positive 9. Right, notice inequality flips because we divide by a negative. Only happens when you multiply or divide by a negative, not just all the time. So the values for x that work out in this particular problem are those that are greater than or equal to 10 or less than 9. What does that look like on a number line? Well, with an OR problem, we're just going to try to look at all the regions of the graph that are shaded. Suppose here's 9 and here's 10. X is greater than or equal to 10 is going to be a closed shaded in area at 10. We're going to be shading to the right. And x is less than 9, open circle, and shading to the left. And so those are all of the regions of the graph that would be less than 9 or greater than or equal to 10. The only numbers really that wouldn't qualify are those between 9 and 10, like 9.5. All right. Hopefully that makes sense to everybody. Again, notice an OR problem is really just shade everything on the graph. We're just looking to see where both of these inequalities happen to land, and we just shade them accordingly. Right? An AND problem is where we're going to look for that overlap to occur. All right, let's keep going. Here we go. Backside. We have an AND problem up at the top. How do I know, it's like a very similar question that we've asked in class. How do I know that this is an AND problem without it explicitly saying the word AND? The answer to that is the fact that this 9x plus 1 is sandwiched between the negative 53 and the negative 26. So this 9x plus 1 has to be greater than negative 53, and at the same time, this 9x plus 1 has to be less than negative 26. So what I can say is just literally break it down that way and say, well, this 9x plus 1 has to be greater than negative 53, and this 9x plus 1 has to be less than negative 26. That makes sense, hopefully. If it's between negative 53 and 26, then it clearly has to be bigger than negative 53 and less than negative 26. Now, just like the OR problem, we have two independent inequalities that we can go ahead and solve and then look at their overlapped area on the number line. If we subtract 1 from both sides on this one, that gives us that 9x is greater than negative 53 minus 1, negative 54. We can then divide both sides by 9 to undo that multiplication of 9 times x and get that x is greater than negative 6. It's our first little piece. So the values of x that'll work out have to be those that are greater than negative 6 and those that are, let's find out. Subtract 1 for both sides. Oh no, is my pen dying? No. We get not, oh man, my pen just completely died in the middle of the video. How embarrassing. Rats. Do I have another black pen? I think so. I know I have a ton of blue pens. Is this black? Subtract 1 from, oh, look at that. Look at that. Coming to the rescue. Fresh black pen, ready to go. Come on. As if you think I'd fall apart in the face of that. Anyway, getting off track here. 9x is less than negative 27. Can overcome adversity, no matter how bad, in algebra. It's not going to slow us down. Divide both sides by 9. We get x is less than negative 3. All right. So the graph of the values for x that work here are those that are greater than negative 6 and at the same time less than negative 3. So we have to take a look and see, well, what values satisfy that? Suppose here's negative 6, and suppose here's negative 3. Values that are, let's do this one first, less than negative 3 means we would have an open circle on negative 3 and we would shade to the left, correct? Can you picture that in your mind? If you were just graphing that one, you'd have an open circle at negative 3 shading this way. If you have x is greater than negative 6, well then you'd have an open circle at negative 6 and you'd be shading this way, to the right. Correct? Because these would be all the values that are greater than negative 6. So what region of the graph is encapsulated by both of these shadings? Well, it's this middle part right here. These are the numbers that would be greater than negative 6 and also less than negative 3. Like negative 5, for example, is bigger than negative 6 and less than negative 3. All right? The last point I want to make about these number line graphs is I'm not going to require you to draw them to scale, in the sense that you don't have to take out a ruler and measure to make sure it's all nice and neat and lined up. If you want to, I'm certainly not going to stop you, but you don't have to. However, you should certainly have on your number line graph that negative 6 is to the left of negative 3, because negative 3 is larger than negative 6. Please don't mix those up and have them opposites, because that not only is it incorrect, but it's also going to throw off your graph in the sense that you'll be shading the wrong things and you'll probably get confused because it won't look like the ones we did in class. So don't let, I don't want you to get thrown off your game like that. Make sure you're putting the smaller value on the left side, the larger of the two values on the right side. Hopefully we're A-okay with that. Now, let's go ahead and jump into the word problems. All right, these again were made by Diana. I think she did a good job making her own word problems. I feel like those are the toughest ones. With equations, sometimes you can just change the numbers and more or less be able to make equations pretty quickly. But to make good word problems, it takes a little bit more effort. So props to her. Anyway, 23 says, Fiona wants to earn at least $30 this week. Her mother said she can earn $8 for organizing the pantry and $3.50 per hour for babysitting. Set up and solve an inequality to determine how many hours Fiona needs to babysit to earn at least $30. So this is one of our linear equation word problems where we have this initial amount as well as this rate going on per hour in this case. So if she earns $8 for organizing the pantry, notice that just happens once. That is a one-time occurrence of $8. Not $8 per time she organizes. It's just she's organizing once, she's going to get $8. So my inequality is going to start out with just a regular old 8. Now she also earns, so plus, $3.50 per hour for babysitting. So how many hours is she spending babysitting? Well, we don't know the answer to that, so we can say that this is plus 3.50, or 3.5 if you prefer, times x, because we don't know how many hours she'll be babysitting for. And she wants to earn at least $30, so that means this has to be greater than or equal to 30. All right. It could be 30, because 30 would be at least 30, or more than 30 would be great too. Hopefully no question as to how we figured that out. Again, 8 is the one-time occurrence, $3.50 per hour. How many hours? We don't know. And she wants to earn at least 30. Now I would solve this inequality by subtracting 8 from both sides. That would give us that $3.50 times x, 3.50x, is greater than or equal to 24. 30 Oh, it's 22. Sorry, 32, 30 minus 8. Jeez, 22. Now we can go ahead and divide both sides by 3.5 to undo that multiplication. Just because it's a decimal doesn't mean we panic and freak out. The process of solving is still the same. We get x is greater than or equal to, break out the calculator here, 22 divided by 3.5. We get that x is greater than or equal to 6.285. So we'll round that up to 6.29. Okay. Just because we got a decimal again doesn't mean that the universe is crumbling around us. Now we just have to apply that knowledge to the problem and say, well, if x is greater than or equal to 6.29, means she has to work 6.29 hours. Well, this is talking in terms of full total hours. So how many hours would it take her to, how many hours would she have to babysit? Well, if x has to be greater than or equal to 6.29, then it really has to be 7 hours. Okay? So you'd be able to say, well, it's 6.29. I guess you could say, like, she has to work at least 6.29 hours. So you could say she has to work at least 6.29 hours. Or if you actually took the extra step to say, well, we could round it up to say she has to work 7 hours, that would be fine too. But hey, you know what? I'm having a little change of heart on that. We could stop and just say she has to work 6.29 hours. That would be like what? 6.25 hours would be 6 hours and 15 minutes. So maybe like 6 hours and 17 minutes or so. All right. Hopefully that makes sense as to how that's done. Last but most certainly not least, problem number 25. I love these problems where we have to kind of dissect a sentence and figure out how to translate a sentence into math. It says 5 less than a number doubled is between 15 and 25. Find the set of all possible values and graph the solution. So 5 less than a number doubled. Think about what that means. A number doubled means we're going to take a number and multiply it by 2, right? Doubling a number, multiply it by 2. And now if I'm going to do 5 less than that, I'm trying to search for a value that's 5 less than that, we're going to subtract 5. And right there, that is a number doubled minus 5. That's 5 less than a number doubled. So hopefully that makes sense how we translate that, right? A number doubled is your 2x, and then 5 less minus 5. Now, what are we saying about that value? Well, we're saying that that value is between 15 and 25. So that means that this has to be greater than 15 and at the same time less than 25. See how it's sandwiched right between 15 and 25? If you do not feel comfortable writing that sort of hybrid compound notation, what you could write instead is you could actually just break it down in your head and say, well, if this thing, 2x minus 5, is between 15 and 25, then that means that 2x minus 5 has to be greater than 15, and at the same time, 2x minus 5 has to be less than 25. Right? Because it's between those. So because it's between those, it has to be greater than this and less than this. Now we can go ahead and just solve these inequalities independently like we've done with all our compound problems. We can add 5 to both sides to get that 2x must be greater than 20. Divide both sides by 2 to undo that multiplication, which gives us that x is greater than 10. And at the same time, add 5. We get 2x is less than 30. Divide both sides by 2. We would get that x has to be less than 15. So at the same time, x has to be bigger than 10 and less than 15. I don't have a lot of space down here, but I guess I can squeeze a number line right up here. If x is bigger than 10, suppose 10 is here on my number line, picture that that would be an open circle and we'd be shading to the right, correct? That's x is bigger than 10. If x is less than 15, picture that that would be a open circle at 15. Where are we? 11, 12, 13, 14, 15. Open circle at 15, and we'd be shading to the left. So what section of the number line is going to get overlapped by both of these shadings? Well, it's going to be this middle part right here. These would be all the numbers. For example, like 12, 13. Those are the numbers that are greater than 10 and less than 15. All right? So problems like these are exactly those that you're expected to do on the summative assessment. We should be able to identify inequalities represented by graphs. We should be able to solve and graph regular one-sided inequalities, as well as compound inequalities. Here's an OR problem. Here's an AND problem. And we should be able to handle word problems as well. Okay? If you have any questions, please do not hesitate to reach out and ask. Hopefully that was a nice little review for you, though, and I really hope that answered some of the questions or cleared up some misconceptions that you had. Best of luck. Study hard. We're here if you need us. The test review, full test review, is posted on Google Classroom as well as the answer key, so please make sure to refer to that as well. But I hope you have a great rest of your day, and good luck, everyone. Take care. Work hard. I know you can succeed. I believe in you. I believe in you. Take care.